Michael, can you hear me?
Yeah.
All right, I can hear you also. Any homeworks to do today, to ask today, Michael?
No, go to electrolysis.
Right, okay. Aryan, can you hear me?
Yes.
I can hear you too. Any homeworks to ask today, Aryan?
No, I did it before tuition.
All right, good, very good. Like that, then we can use it for good stuff, lah. Right? So Mike and Aryan, shall we just jump into electrolysis, lah?
Sure.
Okay, Michael, yes?
Yeah.
All right, okay. So just tell me, Mike and Aryan, Michael, first, where are you with electrolysis right now in the class? Michael, where are you in electrolysis in class?
Hold on, let me see.
Yeah. Aryan, maybe Aryan. Yeah. Aryan, where are you in electrolysis?
We haven't started yet.
All right, okay, understand.
My teacher started speed of reaction today.
All right, that's not difficult to understand. Yeah, but questions might need more practice. So the chapter itself is okay. Right? Okay, good. Yeah. Noah, can you hear me?
Yeah.
Okay. Do you have any homework or questions to ask today?
No.
Same, sorry. Cannot hear you, sorry.
No, we just started a new part of the chapter.
What is that?
The logarithm.
Logarithm. Oh, all right. So no problem. I understand. Right. Then same thing. If there is nothing better to do, then we can do something very useful, which is same like last time. I'm going to ask you to try the prelims question. Would that be okay?
Okay.
Okay. So same thing as last time. You're going to continue from the last thing and going to choose your questions for now. Right? As we get closer to mid-year, we're gonna make our training more precise. But for now, I just want you to get used to the questions you'll be facing. Okay? Right.
Then
so
how
I'll
about for
sorry, you were saying? Sorry?
How about for the new things I'm learning?
How about for the what? Sorry?
The new things I'm learning.
For example, the logarithm differentiation.
Or whatever comes next.
Whatever comes next, you probably can do it very easily if you're talking about integration, because the next thing to come is integration.
Oh, okay.
Right. We already like cover a lot of that during holiday tuition. Right? That's the purpose of holiday tuition, right?
Yeah.
So that's why when you jump to the prelim question right now, you see some integration question, you can already do some. You can already do some.
Okay.
Okay, and that's why we're just practicing for prelim now, because you already cover everything prelim, mid-year. You already cover everything you need for mid-year, something like that. Okay.
Yeah.
So I'm going to follow your working using the video. Right? Choose any question you want. Okay. So Mike, where are you in electrolysis?
We're like, what if the electrodes were like copper? And then it's like, what is it? Oxidizing reduced, but I still kind of don't get that bit wonky on that.
Okay, redox. All right. Okay. So go to the same Jamboard like last time. Still the same Jamboard. Go to page 5 and then write your name using mouse, Aryan and Mike. Okay. Okay, who is that? Sorry, Aryan. Okay, Aryan. Then Mike, who are you? Oh no, Mike is okay. Good. Then Aryan, are you here in page 5 of the Jamboard? Okay. All right. Okay. So Mike and Aryan, let me give you first the bad news of electrolysis, and then let me give you the good news, or rather the benefit. Right? So the bad news of electrolysis is this. There is no other topic which is as hard as this thing in exam. What I mean by this, almost all electrolysis question in exam, prelim, whatever exam that you face, they don't hold back. They just give you the hardest of the hardest topic. It's very weird sometimes, but that's what happened. When you see electrolysis question, you have to think 3, 4, 5 times more than other topics sometimes. More than other topics. So even though you study your electrolysis basics correctly and you understand the chapter and you feel that you can do all the practice question, go to exam and then suddenly, what is this electrolysis question I've never seen before? Right? Now that frequently happens. That's the bad news. Right? So you will see when we finally jump into exam questions. Right? So now let me give you the good news. The good news is this. If you study your electrolysis well, suddenly many other chapters before electrolysis suddenly become stronger, because electrolysis forces you to understand them in a foundational way. So if you have problem with other chapters, it will be revealed by the electrolysis chapter. I'm going to show you very clearly that today. So what I'm trying to say to you is the benefit of studying electrolysis well is not to answer electrolysis question in exam well. They are just too damn hard sometimes. But it's very clear what the benefit is to other topics before electrolysis. For example, Mike, you asked about redox. Your redox is wonky. Suddenly, redox appear in electrolysis. If you can understand the redox in electrolysis, chances are the other redox question you can understand, at least is foundation. So that's the benefit. Right? There's a lot of other old chapters in electrolysis. So I'm going to try to list them down today. Okay. Now, any questions about Mike and Aryan? No, yeah. Now, Noah, I cannot follow your video. Are you okay?
No.
Noah, I cannot follow your video. Are you okay?
Sorry?
I cannot follow or see your video. Are you okay?
Sorry, see.
I cannot
I only
follow.
can hear. I cannot follow you.
I cannot follow your video. I cannot see your video. Are you okay?
Yeah.
All right.
But so, where can I find the exam papers? Really?
Same thing. If you cannot see it from your Google Drive, there's a problem there. But just click on the link I sent to you last time. So the link is like since you cannot use your Google Drive to find it, use that link. Still the same exam paper, right? Because you have only done two, correct? Like then, 2 questions. Cannot? Okay, good. I'll be waiting for your video. So now, Michael and Aryan, what is the first thing to, what do I teach you? The first thing to take note of during electrolysis question? What is the first thing to take note of? Michael?
The first thing to take note of.
Yes.
Whether the electrolyte is aqueous or molten.
No, that's not what I teach you. Definitely not. Not that thing. Not the thing. What is it? Oh, come on.
But it's the flow of the electron.
Yeah, which is determined by the battery direction. Okay, so that's the immediately the first thing that you do, no matter what electrolysis question. Aryan, please draw for us the electron flow. Right. So Aryan, draw for us the electron flow.
Yeah.
Okay, so the electron will go like this, and so the electron will be going in here and going out. That's the important thing. Now, we are already at a level where this is no longer the easy one. The carbon is easy, the platinum is easy because they don't react. You don't have to care about them. Suddenly, this can be something else. Now, we talk about the example, for example, Cu last time. But it can also be Fe, it can also be Pb, for example, right? So I'm going to explain that again today. Now, remember that, yes, Aryan?
Can it also be a highly reactive metal?
Again, this is aqueous most of the time. If you use a highly reactive metal, it's not that you cannot, but the problem is water. The problem is the water, right? So again, it's not that sodium is theoretically impossible, but it's practically impossible.
Yeah.
Right? So we use not so reactive one, like for example, zinc. Can you use zinc? Well, I think you can, right? Because at least it doesn't react with water. At least not practically reacting with the water, right? Okay, now Cu and Cu. One of the effect of having non-carbon, non-graphite, and non-platinum is that you have to consider that they react. Now I'm going to make it simpler for you. This Cu has the opportunity to release its electron, correct? This Cu has the opportunity to release its electron, and this Cu has the opportunity of receiving this electron, right? Who will take that opportunity? Will this Cu take this opportunity, and will this Cu take this opportunity? Aryan. Let's call this the first one, and let's call this the second one. Aryan, are you okay? Can you hear me?
Hello?
Can you hear me? I asked you a question just now. Can you hear me, or is there a problem with your audio?
Sometimes cutting off.
Are you using your headset?
No, I'm not.
My question is, will this Cu take the opportunity to release his electron? Will this Cu? Yes. All right, then. Will this Cu take the opportunity to receive electron?
No.
All right. Now, I will change it to some other metal here.
Wait, no, sorry. Cu plus will not be equal to release.
There is no Cu plus here. Why do you say that
Sorry,
this
Cu.
Cu is a Cu plus? This is Cu metal. Is there anything Cu metal that is a Cu plus? Can Cu plus or Cu2 plus be metal?
Oh no.
No. So if it is Cu metal, Cu. This is your basic set. This is why electrolysis is testing your sec 3 and sec 4 foundation. This is why, right? Don't see electrolysis as only electrolysis. So, Michael, you're clear, eh? Cu metal must be Cu lah, not Cu plus. Not Cu.
If it's Cu2 plus or plus, then it's an ion already. Yeah.
It's an ion, and it won't be in metal form. It'll be probably soluble here. Okay.
Yeah.
Right. But Aryan is saying this. Aryan is saying this Cu, which is not plus, this Cu will take the opportunity to release his electron, so he will become Cu2 plus. He will want to become Cu2 plus, and therefore he will kind of leave his metal form and kind of dissolve it, which is a fancy way of saying he will react basically. He will react. So I agree with Aryan. This Cu will jump at the opportunity. My question is, this Cu, since no Cu will want to take the offer of the electron, extra electron, then I go to Michael. Let's say I change this Cu to Fe. Let's say. So this Fe is now here. Will this Fe take the opportunity of receiving this electron?
Receiving.
Yeah, because the flow of electron is like this. So he's offered the opportunity to take this electron to himself. No. Well, I hope both of you know why. So Fe doesn't work. Give me another example of metal, please, Aryan.
Zinc.
Okay, zinc. Aryan, will zinc, since we now replace this with zinc, will zinc take the opportunity of accepting an extra electron or more than one? I don't know, whatever. Will he?
No.
No. Michael, do you agree?
Sorry, can you repeat that very quick?
Will zinc receive the opportunity of the extra electron? Right, good. Then my final question to you in this matter, everybody, both of you. What metal can we put here so that the metal will gladly receive and use this extra electron? Any metal will do that. No? Aryan?
No.
Therefore, since your sec 3 is correct and very good, therefore, whatever you put here will never react.
Not even with the electrolyte.
No. I mean, it's possible to react with the electrolyte if the electrolyte is acidic or basic, but that's why we don't use acidic or basic electrolyte. It is very confusing if you
That's why the electrolyte is always an ionic bond.
A salt. So which tends to not react with the metal. So again, because the purpose is not to do that. Correct.
So using the most common electrolyte, which is a salt, right? Like I don't know, NaCl, right?
Okay, let's say NaCl, right?
Yeah, by this theory, right? Then the anode will not react.
Yeah. Is this an anode?
Sorry, the cathode.
No, this is a cathode. Yeah. So this guy here, which you correctly say is a cathode. Why? Because this is a negative, so the positive will go there, right? Cation. No matter what you put in cathode, no matter, it will not react. Now, still, if you put a reactive metal, it'll react with water lah. So that's why again you avoid reactive metals. But that's just they kind of consider common sense, like don't do that lah, right? Yes, Aryan?
Okay.
If you put like the reactive metal in a molten,
even more problematic. There is no water, but for example, because of the high temperature, molten high temperature, the reactive metal will react with the oxygen in the air. Another problem, because it's too hot already. Secondly, it will melt because of the high temperature. Again, we're talking about 800 degrees. It's a big problem. Not a lot of metal can withstand 800 degrees. So even though the reactive metal don't react, it will melt most of the time. That's just how reactive metal is. They are very easy to melt. So again, you don't put reactive metal in electrolysis. Why? Here's the logic. Here's the logic, so that we can kind of delve deep in. The reason is because electrolysis is actually the way to make reactive metal, not to react reactive metal. Electrolysis partially is invented partially to make reactive metal. For example, to make sodium metal, not to react sodium metal. You learn how to make sodium metal, molten sodium metal, at the first electrolysis example. Remember the molten NaCl. Do you still remember that, Aryan?
Yeah.
Right. So to do that, you don't need a sodium electron. You just need the carbon or the platinum electron. So I give you the chemical reason why you don't use reactive metal, because they will react, right? And that's not the. But I give you also the practical reason, because we don't want to react reactive metal. We want to make reactive metal sometimes. So we do that with electrolysis. And the way to do that is not to make the electrode reactive. We're trying to make it something like that. So let's assume that we don't have it at the start. Will that be okay, Aryan and Mike?
Yeah.
Yeah.
Right. So now, since I have explained to you and you have accepted that you can put any metal here, again, just not the reactive one. Just not the reactive one. Now, I'm going to put your handphone here, Michael, your handphone. Now, tell me, your nice handphone, the body of the handphone, not the casing, never mind the rubber casing, okay? So the body of your handphone, is it plastic or is it metal?
The what of my handphone?
The body.
Oh, the body.
Yeah.
I think it's metal.
Tell me what metal might it be?
I have no idea, but it's definitely not iron.
Oh, definitely not. Definitely not. Doesn't work. Give me the brand. Give me the brand of your phone.
Samsung A52s.
Oh no, that's plastic.
I don't know.
Yeah. So I will pretend that you are using an old design, like an iPhone old design, where the casing is made of magnesium, quite strong. Just pretend. Magnesium is almost reactive, but it doesn't react very quickly with water, so you may put it as an electrode. So again, this is your handphone. Aryan, so far so good. This is an old iPhone, which is made out of magnesium, and for some weird reason, I am plunging the phone halfway in the electrode and then connecting it to a battery. Okay, handphone. It's an old handphone, so who cares? Now, I am also going to replace the electrode with, well, CuSO4. No explanation given yet. This will be Cu2 plus and SO4 2 minus. And this guy, I will specifically put Cu. Specifically, okay? Specifically put Cu. Now, let us investigate what happened when we put the battery on. Okay, let's investigate. Again, positive go there, negative go there, H plus also go here, and OH minus also go here. Aryan, who is the competitor here?
The Cu2 plus and H
the
plus.
H plus. Michael, who will win?
The H plus.
Okay, no. This is testing your reactivity series, another topic, right? So far, we have already been testing Sec3 topic and also reactivity series, correct? Your reactivity series, please, right? So very quickly, Michael.
It's U2 plus because the jump is
it's slightly less, right? CO2 plus. Yeah. So CO2 plus win. Again, in O level, that's all you need to say. You don't need to say, but H plus will also win and whatever, they don't care, right? So CO2 plus will gladly accept the electron, correct? To electron to become what? Cu lah. Correct? To become Cu. Now, tell me, Michael and Aryan, where does this Cu happen? where does this Cu appear? Where?
The magnesium electrode, like the
Very
outside.
good. Very good. Very good. Here. Here. Suddenly, Michael and Aryan, what happened to our old iPhone after a while?
Electroplated.
Yes, this is called electroplating. Your iPhone is now copper coated. Very nicely copper coated, by the way. This is a nice. If you clean your handphone properly, you can do this at home and get a very nice copper color if that's your thing, right? So copper. But however, this doesn't last long because the copper plus will run out. Make sense, Aryan and Mike? It will run out. Because the electrolyte doesn't contain that much. This is becoming a solid, this will be a solid. So let's look at anode. Why anode? Because the anion goes there, right? Who are the competitor, Aryan? Who are the competitor here?
The SO4 2- and OH-.
No, you forgot one more. Please, you forgot one more. You forgot one more.
Cu.
Yes, because the Cu will also gladly release his electron. So he's a competitor. Understand? Right? Now, again, in O level, they don't explain why, but SO4 2- will never win. Okay, there you go. Will never.
I heard like somewhere or something. It's like the least reactive or something.
Yeah. It can win, but in O level, let's just say he never win. But like keeping it simple. It can win under very rare circumstances because it is very difficult for him to win. Again, in O level, whatever, he doesn't win. Understand? So that means if you see something like this, NO3- also never win. If you see PO4 3- also never win. Just never win. Make it simple. Okay, Michael and Aryan. Okay, too complicated. Too complicated for him to win. So now we're only left with OH- as a competitor and Cu as a competitor. Michael, who will win? Thinking too long. OH- as a new sub, right? So there are two reactivity series. This is a new reactivity. This is a negative reactivity. This is a positive one. And look at the Cu. The Cu, if he wins, will become Cu2+, correct?
Yeah.
OH- needs to jump up and Cu needs to jump down. Come on. The winner is clear. The winner is clear. Come on.
Oh,
Michael.
Cu.
It's always Cu because Cu jumps down. OH- jumps up. No matter what, jump down will always beat jump up. Always. All the time.
Oh, okay.
All the time. So Cu will always win. OH- have no chance at all. Understand, Aryan?
Yeah.
Right. So logically, we write minus to E, but you know what? Chemistry hates minus, so we change it to this plus Cu plus. Okay. So again, the Cu is voluntarily and happily releasing its electron to the battery, and he becomes Cu2+. And where does the Cu2+ go, Michael? Where does the Cu2+
go?
Goes to? It goes to the electrolyte, right? So basically, the anode here, right, is being consumed. You will see pits and holes after a while because the Cu becomes Cu2+ and enters the electrolyte solution. He no longer stays metal. Aryan, do you understand?
Does it keep replacing the Cu2+, like converted to Cu?
Yes. So the Cu here will enter the electrolyte, replacing the Cu2+, so that we can always electroplate this. Basically, this goes here, this goes there. So we can say that this goes there, Basically, we can say that, We can say that. But through the electrolyte water, he doesn't go directly. Obviously, it's not touching. Okay, understand?
Yeah.
So if you put your handphone half in, then you have a half magnesium, half copper. So you just put all in, then you'll get what you want. You get what you want. Okay. Why? Because whatever you put here doesn't matter. It will not react. it will not react. Nothing will happen to the magnesium. Magnesium is not a competitor. But be careful what you put here, because he may be a competitor. He may be a competitor. So far, so good. Understand?
Yeah.
Yes.
Right. So this is the most interesting, I feel, the most interesting and the most practical application of electrolysis, which is electroplating. We're just plating with the help of battery. And whether you believe it or not, we can easily do this at home. Just have to buy some of this. It's not toxic. Put whatever you want here and buy, just tie a thick piece of wire, pop with a normal battery. You will get electroplating in whatever you want to do. Like really, really just like that. Simple. Okay. Now, further question for both of you. Oh, sorry. Before that, I want you to repeat. I want you to repeat drawing this, Michael and Aryan, and I want you to write down the equation on both places, and then I'll explain redox to you, Michael. Okay, okay. Now, Michael, I will now erase this. So everybody, please. Aryan and Michael, please draw and rewrite the reaction. Noah, any questions or what?
No.
Can you zoom out a bit, please, so I can follow better? Can you zoom out?
Ka,
Yes.
do you use the smartphone example or?
Do you use the smartphone? No, don't draw here, Mike. Don't draw here. I'm asking you to draw on
Oh.
paper. Don't draw on paper. Don't draw here. It's hard to draw here. Is that right? So show me your video, Aryan and Michael, and then just draw on paper. You can use the smartphone example. That's fine. That's fine. For now, that's fine. Now, Noah,
I just write up magnesium.
Can, no problem. Okay. Noah, why do you choose in this question? Why?
Is there a specific chapter I'm supposed to do?
Limit your chapters to the ones in mid-year first now.
Okay.
I mean, I know that you want to, if you want to practice in this, that's fine, but that's like after mid-year also can. I mean, something like that. Make sense? So your mid-year is 3 go and differentiation and some integration mostly. You focus on that first. Okay? Don't do the other one first. Also linear law and CG is in, but no need to do that first. Do the other one first. Okay? So don't do it in this first. You look fine. Don't do it first. Okay. Aryan, you still need to write the H plus and OH minus to remind yourself. You still need to do that because it's still equals. It's still good practice to do that. Good. Now again, Aryan, normally you will plunge the smart moons fully in. I was just drawing half just to give it. But usually you just put everything in usually. Yeah, something like that. Yeah, everything down. Yeah. Okay. Now, Aryan, for presentation purpose, this Cu2 plus 2E, you must write, is it at cathode or anode? That's the formal term. So you must be able to write that. Is it at cathode or at anode? Again, the definition of cathode is where the cation go, right? Definition of anode is where the anode. Okay, good. Right. So all you have to do, Aryan, is figuring out the other reaction. Okay. In your mind, think about a competitor. You can even write down the competitor and decide who will win. Oh, Noah, is there a proving question? Really? Proving question? Is it no?
Yeah.
Oh, spicy. Okay. Give it a try. Spicy. Spicy. Okay, Aryan, can you pull up a bit? Cannot see the bottom one. Aryan, go up a bit. Okay, nice. Okay, now Aryan, let's see whether you can answer Mike's question. So by right, in every electrolysis, there is a redox reaction. So some will reduce and some will oxidize. Michael and Aryan, look at your cathode and look at your anode. One of them is reducing, one of them is oxidizing. Don't memorize. It's very obvious who is reducing and who is oxidizing. Please, who and who?
My cathode is reducing and my anode is oxidizing.
All right, Michael. So for presentation purpose, you must write down who is the cathode and who is the anode. Like this reaction at where and this reaction. You have to write down. No, at the left of the reaction. At the left of the reaction. At the left of the reaction. The reaction. So these two reactions you must write at cathode which one, at anode which one.
Oh.
So Aryan, I hope it is obvious that the cathode is reducing and the anode is oxidizing. Obviously, right? At anode, okay. Then again, Mike, who is reducing and who is oxidizing? Again, I hope you can see it instead of memorizing it. Right. So Mike, you and Aryan actually answer differently. So your anode and cathode is the same, but Michael say at anode is reducing. Aryan say at anode is oxidizing. So we have a bit of a yeah. I'll look at the cathode instead. So the cathode, Aryan say is reducing, but Michael say at cathode is oxidizing. So Aryan, why do you think the cathode is reducing?
I'm the one that say cathode is
because
reducing.
No, you say, Michael, your cathode is oxidizing. You wrote it down that way.
Oh yeah, wait.
Hello.
Wait.
The cathode is reducing because the oxidation number of the copper decreases from 2+ to 0.
Yeah, very nice English also. Right? Obviously. Another obvious sign is that electron. If you're receiving electron, you must reduce negative. You're receiving a negative. If that makes sense. Whereas in anode, you are losing electron, right? Okay, -2e. So you must be oxidizing. Okay, so Mike, that means you are now the same. Clear, yeah?
No, I mistook this for cathode again.
Again, don't.
This for anode again.
Again, what is the best definition of cathode, Michael?
Cathode
is where
the positive ions
the cation go. Yeah. So you look at it from that point of view. Don't memorize things in electrolysis. Too easy to get wrong. Understand, Mike? If you do understand, your benefit is like clear in other topics. Like clear. Don't follow people who memorize electrolysis. If your teacher asks you to memorize electrolysis, do not do that. Understand it. Please, if you want to derive any good benefit from studying. Okay, so Michael and Aryan, we're approaching the last part, so I'm going to ask you a few questions. For the anode, both you say is oxidizing, right? So is it possible in some cases for the anode to actually reduce? Is it possible or not possible? Think about it, Michael and Aryan.
Wait, wow, can you repeat that?
Again, both of you say cathode reduce, anode oxidize. I agree with you. Okay, all good and stuff. Is it possible for that to flip? So, is there any scenario where cathode oxidizes and anode reduces? Is it possible for that to happen or not possible? Think about it, Aryan and Mike. Noah, can you see your working? Just pull up a bit. The way you do it is interesting, but what is your goal, Anwar? Because you don't write the right-hand side, it's difficult to work without a goal. What is your goal? No. You have to keep the goal in mind. In this case, I think the right-hand side. If you don't have a goal, what you're doing is not good at all. Your goal is something simple, tangent square x. Tell me, Noah, why do you decide your first step to be like this? What do you hope to achieve?
I don't know what I'm doing.
Yeah. Now, of course, proving is trying lah. But if this is the way you try, it's not very good. Because I feel, don't cancel, please don't cancel. Never cancel stuff. Waste of time. Waste of time. What you're lacking is you don't look at the goal. Now, look at your starting point, 2 sine 2x, blah, 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 sine 4x, and look at your goal. Your goal is tangent square x. You can look at your goal in a few ways. You can look at the goal and say, oh, I don't have a denominator, so I must eliminate the denominator. That's one way to look at it, correct?
Yeah.
There's also another way to look at it, because there's always a few ways to look at it. My way of looking at it is, for example, oh, it's 2x and 4x, but the end goal is only x. I will start focusing on that first. It's my freedom to focus on whatever I want to first. So I'm telling you, there's another way. For example, try to make the 2x into x first. Maybe that will lead you somewhere also. Make sense?
Sorry?
Look at the goal. The goal is tangent square x.
Yeah.
The starting thing is blah, blah, blah 2x and blah, blah, blah 4x.
Yeah.
Change those 2x's and 4x's into x. That's another approach that you can take.
Oh, okay.
Understand? Because why? Because you're looking at the goal. Oh, the goal is like this. Okay, maybe I'll try that.
Okay.
Understand? Please give it. Michael and Aryan, are you ready with an answer? Aryan?
Yeah.
Is it possible?
I don't think so.
But why don't you think so?
Wait. Wait, what's...
Yes, Aryan? Yes, Aryan, sorry, you're saying?
Do you draw something in the Jamboard?
No. I was asking a question. Do you hear what? Did you hear my question like 3 minutes ago?
I don't think so.
In your phone, have I been silent for the last 3 minutes?
Yeah.
Michael?
I think the connection problem.
Right. I'm checking the connection problem with Michael. Michael, have I been silent for the last 3 minutes?
No.
Did you hear my question, my last question?
Yeah, is it possible for a scenario where the cathode is the one that's oxidizing?
Okay. Michael, did you hear me when I talked to Noah after that?
Yeah.
Okay. Aryan, you didn't hear the question. Am I correct?
Yeah.
You also didn't hear me talking to Noah.
Yeah. I only heard like bits and pieces, like it was cut off.
Right now?
Not right now.
Can you fix? I'm assuming that maybe it's possible to make your connection better. I'm just assuming that. Is it possible? Does this happen last year?
No.
Has this been happening this year?
Yeah, sometimes.
I don't like it. Michael, so
Yeah.
Aryan, I'm going to repeat the question one more time. The anode is oxidizing. Is it possible in any scenario for the anode to be reducing? That's my question. Okay, Aryan?
Yeah.
Now, Michael has been thinking about this. Michael, what's your opinion?
My opinion is that no, it's not possible.
Okay. Why do you think not possible?
Because, like, you know, like for the cathode to be the one that's oxidizing,
Okay.
right? Then it needs to be one of the things need to be a 2- or a minus ion. instead of a plus, and there's no metal that's a plus. Or sorry, yeah, there's no metal that's a minus ion.
So you're saying that a Cu cannot go into Cu2 minus.
A Cu cannot go into Cu2 minus.
That's what you're saying, right?
I don't think so.
Yeah, I don't think so. No. In O level, no. Yes, I can affirm you that. And in A level also, in A level only in very, very specific circumstances. And that's very specific. So the answer is basically no lah. No. So in real life also no. No, Cu don't become Cu2 minus. 99.9999% of the time. Okay. In O level, 100%. Right.
Okay.
So I understand your reasoning, not bad. Okay, I'll give you the full reasoning and then we'll close. Aryan, right? Not bad.
Yeah.
Okay. Again, just by looking at this, Aryan, who is the cathode? Can you tell immediately who the cathode is and who the anode is?
Yeah.
Which one is the cathode?
The cathode is the one on the right.
Good. Why? Why?
Because it's like the electrons are flowing out.
And the positive will go there lah. Because why?
Yeah.
Because this is negative lah, right?
Yeah.
Negative. Now some people will memorize this as the cathode is negative. Some people will do that. Don't do that. I'll give you the reason later. Never memorize it that way. It's very confusing after a while. There's something else happening after this, right? So here's the cathode and here's that. I'm glad that you don't memorize it that way and don't memorize it that way. Now, here's the reason, a very clear reason why the cathode will always be reducing, because the cathode will always, it is no way that this doesn't happen. Cathode will always receive electron or pass through electron. Anode will always release electron. So if cathode is receiving electron, there is no other way. He must be reducing. No other way. You cannot change this here. You cannot change this there. This will always be called cathode. This will always go here. This is always negative. This is also. That's why I ask you to always think about the battery first, because the battery governs everything. So cathode will always receive electron, anode will always release electron. Therefore, cathode will always reduce and anode will always oxidize. Some people memorize this. I don't think you should. Just understand. Any other question, Michael?
No.
Good. If you are clear, then Aryan, congratulations for finishing the basics of electrolysis. We can jump to the exam question next time. Michael, I think in Sunday, if we jump to the exam question, you will be more than prepared. Just about the right tempo as your school. Okay.
Yeah, sure.
Okay. So Michael, Aryan, if there's nothing else, I'll see you on Sunday. Do your homework first and ask your homework question so that I can teach you more electrolysis. Okay.
Yeah.
Okay. I'll see you on Sunday. Now, Noah, show me your working. Good. Are you stuck for this one? Right. Now, before we talk about this is probably going to be long. Why do you choose proving question? Why?
Because there's the next question I came across and from midyear topic.
Is proving question your strength or like you're reasonably
I was still good at it.
I mean, so happen this one is a bit hard lah. So happens lah, I suppose lah. So happen. But you stop very early, so maybe for a hard proving question, you are not very good at it. But remember, it's hard. It's a hard topic and it's a hard question, right? So what do you want? Are you very curious? Do you want to know how to do it, or do you want to think about it yourself, or do you want to do other topics first? What do you want?
I want to know how to do this.
Okay. Okay, then the first thing I think that you want to try is this. try to change the 4x into 2x first, which is what you have done. But you don't do it that way. You do it another way. Here, you're using the 2 sine 2x method. No. There is another way of doing it. And I feel that you're missing that. You're missing it. Do you know the method I'm talking about?
No.
I'll give you the hint. Go to the last Jamboard of yours, Noah, at 20. I think at 27, is it? Yeah, because 29 you don't have. Go to 27 Jamboard, page 3, quickly.
Okay.
If you forget, you tell me, I'll tell you. The cosine 2a identities, there are 3 forms. What is it? If you forget, tell me.
The cosine square.
What?
Cosine square x minus sine square x.
Yeah, so in this case, it's a. So there are 2 more forms.
Then 2 cosine square x minus 1.
A in this case, and then the other one.
A. And 1 minus 2 sine square a.
Okay, now to prepare for this question, I'll change this to. Oh my goodness, you cannot. I'm sorry. Maybe I made a mistake. Sorry, maybe I did make a mistake. Oh, cannot. If we change this to 4x, it will be 8. You cannot. Oh wow, that means I will try something else. That means I'm going to try something else. Okay, I'm going to try. Shall I? Yeah, I'm going to try this to see what happens, right? So if this is 2x, this is 4x. Agree?
Which Jamboard again?
27 Jamboard, page 3. Goodness me, if you haven't seen it, you must tell me immediately. Don't wait. Don't do that. Yeah, tell me immediately. Yeah. Tell me immediately. Don't wait. Don't wait. So are you here?
Yeah.
Are you here? Right.
Yeah.
So do you see the cosine 4x and this thing?
Yeah.
Okay. So originally this cosine 2a and this 1 minus 2 sine square a, right? Okay. Then I'll change this 2a to 4x and therefore this is 2x lah.
Okay.
Wait. Can you no? No, I'm sorry. Actually, no. We probably shouldn't do that. Think carefully. Yeah, okay, I'll cancel this. So for now, I don't think I should be doing that. Instead, we'll be doing the normal thing, right? So I'm focusing on the bottom one first. 2 sine 2x plus sine 4x will be 2 sine 2x cosine 2x, right? So at least there's 2x and 2x, okay? No, answer me please. Don't be muted. Yeah. Don't mute please. Don't miss. Don't waste both of time. So I see that there's a 2 sine 2x here and there's a 2 sine 2x here. So what can you do?
What's it called? Bracket. Factorize.
Yeah. So do something like this, please, quickly. Change your sine 4x into this. The bottom one. Yeah. Change your 4x. Quickly. Come on. We're already over time.
top as well, or don't need?
Factorize, please. Factorize, please. Okay. Factorize. The top one later. Top one. Just leave the top one later. Don't write things. Don't write things on the top one. You're wasting time. Don't do things on the top one. You're wasting time. There's no value in that. No, there's no value. Just do the bottom one first. Because what we want at the start is to see whether it works or not. Stop writing things that doesn't give you an idea, right? Okay. So now the top one. Can we do something similar?
Yeah.
All right, let's do that. Now then do that. Now you have an idea. See whether it works or not. Do it. Do the top one. Right. Is it useful to do this? That's what you want to know. Okay. How can it be useful? Right? How can it be useful? Why do you like it? Okay, get rid of it. And you like to get rid of it because it becomes simpler, right?
Yeah.
Right. So on your third try, you have something that might be useful. Still not sure yet, yeah? Might be useful. You get rid of it first?
Yeah.
Get rid of it first. So, and then on this third try, since this seems to be better than the first or second one, get used to this. Everybody will try first one, second one, then maybe the third one, you'll get something useful. Okay, so I'll leave this to you. See whether you can go to tangent square x or not. At least this is simpler. Fair enough?
Yeah. Okay,
so that will be your homework, but maybe next time don't do the proving one, maybe, especially when it seems very hard. Okay, so here's your homework. I do expect you to either be successful or to at least try a few things before you give up. Okay. See you on Sunday. Do your homework first, then you can ask your homework and then continue practicing your midyear. Okay.
Okay.
Bye.